Welcome to From Repetition to Adaptation, Robotics Breakthroughs in October 2025. In this episode, we explore the latest advances in robotic intelligence, focusing on insights from 37 new robotics papers published on October 9th, 2025. We will discuss how robots are learning to improvise, adapt, and collaborate, highlighting DEX-NDM by Leo and colleagues as our featured paper of the day. Can robots truly improvise, or are they limited to blind automation? Most industrial robots can flawlessly repeat tasks, but falter if an object shifts by even a few centimeters. Imagine a robot chef who can adapt to a slippery pan without human intervention or code. The question arises: what if robots could learn and adjust with the curiosity and flexibility of a child, exploring new environments and improvising solutions in real time? The quest for flexible machines is at the forefront of robotics research. 37 new arXiv preprint server cs.RO papers have pushed the boundaries, helping robots sense, decide, and learn. Robots are no longer confined to factories. They are entering homes, hospitals, and oceans. Our goal is to translate these technical breakthroughs into accessible stories and insights, making the latest research relevant to engineers, students, and people around the world, and anyone curious about the future of robotics. Robotics is best understood as a technological orchestra blending mechanical engineering, artificial intelligence, neuroscience, and design. Each discipline plays a unique part, creating a harmonious whole. The central challenge remains: building machines that can sense their environments, plan their actions, and adapt to unexpected changes. Today, robots are increasingly found working alongside humans in diverse, unpredictable, and complex real-world settings. The first major research theme is data-driven learning, providing robots with cookbooks of knowledge. FastUMI 100K, introduced by Zhang and colleagues, is a dataset containing over 100,000 real-world manipulation demonstrations. Robots are learning by example, much like studying family photo albums, where large datasets compress years of hands-on experience. This approach enables not only imitation, but also creative problem-solving, allowing robots to generalize from demonstrations to new tasks. The second theme is Embodied Intelligence, robots that can dance with the world. IntentionVLA, developed by Wang and collaborators, enables machines to infer human intent using both vision and language modalities. Robots now reason about their own limbs, their surrounding environment, and the people with whom they interact. The analogy is that of teaching a dancer to improvise on a crowded stage, blending vision, touch, and language for richer and more context-aware interactions. The third research theme is safe and adaptive control, equipping robots with a sixth sense. New algorithms, such as those proposed by Kim and colleagues, allow robots to predict slippery surfaces or anticipate collision risks. Like a hiker adjusting each step on icy terrain, these robots adapt their paths in response to environmental changes. Advanced safety metrics extend beyond traditional benchmarks, ensuring that robots can protect both themselves and those around them in dynamic and hazardous settings. Several key findings from the frontier of robotics research illustrate how these themes converge. DEX-NDM by Liu et al. Achieves sim-to-real transfer for dexterous in-hand rotation. Concept-driven exploration, presented by Singh and colleagues, utilizes vision language models to guide robotic exploration. FastUMI 100K enables robust learning from real home environments. NovaFlow by Patel et al. Demonstrates zero-shot task learning from video data. Additionally, Chang and collaborators introduce new safety metrics for evaluating self-driving robots, offering more reliable assessments of uncertainty and performance. The featured paper of the day is DEX-NDM by Liu and co-authors, which tackles the challenge of bridging the simulation to reality gap for robot hands. The core achievement lies in teaching robots to rotate unseen objects with dexterity, Policies trained in simulation often fail in reality, but DEX-NDM introduces a joint-wise neural dynamics model for effective adaptation. The approach decomposes the problem into manageable, finger-level components, making sim-to-real transfer feasible for complex in-hand manipulation. A technical deep dive into DEX-NDM reveals its innovative use of joint-wise neural dynamics. Each joint of the robotic hand is modeled individually, utilizing low-dimensional latent variables to represent the influence of the entire system. This decomposition reduces complexity, allowing each finger to play its part within the ensemble. Autonomous data collection enables the robot hand to explore new objects and wrist orientations independently. With only a modest amount of real-world data, DEX-NDM achieves robust sim-to-real transfer, significantly enhancing adaptability and generalization. The impact of DEX-NDM is substantial, moving the field toward true generalist robot hands. The system adapts to new objects and orientations, not just those encountered during training. Reliable teleoperation becomes possible, where human operators can guide the robot, while the adapted policy manages the intricate details of manipulation. This work advances the state of flexible, general-purpose robotic manipulation and underscores the effectiveness of combining deep learning with innovative system design. Looking ahead, the next leap in robotics involves collective robotic wisdom. Future systems will adapt and share experiences in real time, learning from one another like a flock of birds adjusting to wind conditions, with each bird benefiting from the knowledge of its neighbors. This vision emphasizes symbiosis, where robots augment human abilities, undertake dangerous or repetitive tasks, and operate as teammates rather than replacements. The field is moving toward a hopeful future where robot collaboration and adaptability drive societal progress. In conclusion, the road ahead for robotics is a journey fueled by curiosity. Advances in data, intelligence, and learning are propelling rapid progress. Contributions from Liu et al., Zhang et al., and others are steering the field toward truly adaptable robots. Despite remarkable achievements, challenges remain in achieving robustness, safety, and resilience against real-world unpredictability. The invitation is open. Your curiosity and engagement could ignite the next breakthrough in this dynamic field. Join the journey and help shape the future of robotics. This presentation was synthesized by combining advanced artificial intelligence tools and human expertise. Content was generated using GPT 4.1 by OpenAI for summarization and narrative construction. TTS synthesis was performed by OpenAI, and visuals were described for Google image generation. A human expert reviewed the final synthesis to ensure accuracy and clarity. While every effort has been made to maintain fidelity, some oversights may exist. References are provided for all cited works to support independent verification. Stay ahead with AI Frontiers by subscribing for the latest news and breakthroughs in artificial intelligence and robotics. This channel, AI Frontiers, invites you to join a community of curious minds and innovators. In this podcast, we bring you the latest breakthroughs in computer science and AI straight from arXiv. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.